In this video, I will talk about RC parallel circuit. I will show you the derivation of admittance equation of this RC parallel circuit. I will show you the admittance in terms of branch impedances of the network. Finally, I will draw the admittance diagram and the Phasor diagram or current triangle using step-by-step method. In this circuit, we have this resistance R and this capacitor C. One end of this resistor R and one end of this capacitor C are connected at this point. Another end of this resistor R and another end of this capacitor C are connected at this point. So they are connected in parallel. So this is RC parallel circuit. This RC parallel circuit is connected across a sinusoidal voltage source, as this is a sinusoidal alternating signal. Therefore, instantaneous voltage will be Vt equal to Vm sin omega t. Let's say the RMS phasor of applied voltage is vector V, and that will be equal to V phase angle 0 degree. This will indicate the RMS value of applied voltage and this will indicate the phase angle phi V. So I can write it like this: Vm over root 2 RMS value phase angle phi V is equal to 0 degree. Okay, and the RMS phasor of total current will be I. Okay, now see, in this branch we have this resistance R, in this branch we have this capacitance C. Let's say this is our branch 1, therefore this branch impedance will be ZR. ZR will be equal to R, and this branch impedance will be ZC, that will be equal to minus JXC. We know that XC is equal to omega C, so we can write ZC equal to minus J into 1 over omega C. The branch impedance of this branch is ZR, which is equal to R phase angle 0 degree, and this branch impedance is ZC, which is equal to minus JXC. Now see, we are applying voltage V across these two terminals. Therefore, I will get current IR flowing in this branch. I will get current IC that will be flowing in this branch. Therefore, using Ohm's law, we can calculate the current IR and IC. The current IR is the current that is flowing through the resistance R, and the current IC is the current that is flowing through the capacitor C, and we will get that by using Ohm's law. IR will be equal to the applied voltage V over impedance ZR. Therefore, it will be V over R phase angle 0 degree, and IC will be equal to V over ZC. We know that ZC is equal to minus JXC. If I take minus here and J square here, we know the value of J square is minus 1. So this minus 1 will get multiplied with this minus sign, which will be plus. So it will not change any value here. So I can write this into this, minus J square over V minus J XC is equal to 1 over omega C. So finally I will get the current through the capacitor, which is IC equal to V into J omega C. Now see, at this point the total current I is entering. The current IR and IC are outgoing. So if I apply Kirchhoff's current law at this point, which I have denoted as node A, if I apply Kirchhoff's current law at node A, we will get I equal to IR plus IC. We know that IR is equal to V over R and IC is equal to V into J omega C. Therefore, if I take V common from here and here, I will get I equal to V into 1 over R plus J omega C. Now see, we can represent this 1 over R plus J omega C with a new term, which is known as admittance of the circuit. Admittance indicates the easiness of current flow in a circuit. The higher the admittance in a circuit, the greater the current will flow in that circuit. So the admittance Y is equal to 1 over R plus j omega c in case of RC parallel circuit. See, Y will be a complex number because here we have 1 over R plus this j. This is complex operator, so that will be complex admittance. Complex admittance Y will be equal to 1 over R plus j omega c. See, we know that the reciprocal of resistance, or 1 over R, is the conductance, and in case of capacitance, the capacitive susceptance BC is equal to omega c. So we can write down the admittance of this RC parallel circuit equal to G plus J BC, where BC will indicate the capacitive susceptance. And in case of RC parallel circuit, the capacitive susceptance will always be positive. Okay, just remember this, capacitive susceptance will be always positive, and G will be the conductance of the circuit, and that will be the reciprocal of the resistance, and the susceptance is BC equal to omega c. When we calculate inductive susceptance, BL was equal to 1 over omega L, and capacitive susceptance is BC, which is omega c. Okay, some people like to calculate the total admittance using the branch impedances. In the resistive branch, the impedance is ZR, which is equal to R. In the capacitive branch, the impedance is ZC, which was equal to minus JXC, or 1 over J omega c. In that case, as ZR and ZC are connected in parallel, the total impedance can be written as 1 over total impedance equal to 1 over ZR plus 1 over ZC. If I take the LCM, I will get ZR into ZC over ZR plus ZC. Then if I take the reciprocal of 1 over Z, I will get Z equal to ZR ZC over ZR plus ZC. Now see, the total admittance is the reciprocal of the total impedance Z. Therefore, Y will be equal to 1 over Z. If I put the value of Z here, I will get ZR plus ZC over ZR into ZC. ZR is equal to R, and ZC is equal to 1 over J omega c. So if I put those two values, I will get R plus 1 over J omega c over R into J omega c. If I take the LCM and cancel out the terms, I will get 1 plus J omega RC over R. Therefore, if I separate out the terms in the numerator, I will get 1 over R plus J omega c. The total admittance will be equal to 1 over R plus J omega c. We know that 1 over R is the conductance, which is G, and this omega c is the capacitive susceptance, which is BC. Therefore, I can express the total admittance Y equal to G plus JBC. This is how we use the branch impedances to calculate the total admittance. Now I will show you how to draw the Phasor diagram or current triangle of parallel RC circuit. To draw the Phasor diagram, at first we have to choose a reference phasor. Usually we choose that quantity as reference which remains same throughout the circuit. In the circuit, the voltage V remains same across the resistance R and the capacitance C. Therefore, the voltage V will be our reference phasor. With respect to this reference phasor, we will draw current phasors IR and IC. After drawing IR and IC, we will draw two additional equal phasors. To draw parallelogram, and the diagonal of the parallelogram will be our total current I. Okay, now see, take the voltage V as reference phasor. We will indicate that V as OA, as it is common in both R and C. We will take OA in X direction. So let's say this is our voltage phasor V. After drawing reference phasor, we will draw IR and IC phasor with respect to reference phasor. If I have a resistor R here, if the current through the resistor is IR and the voltage drop across the resistor is VR, you will see in case of resistor the voltage VR and IR will go in the same direction. Here the voltage across the resistor is V and the current through the resistor is IR. Therefore V and IR will be in phase. That means V and IR will go in the same direction, and we will indicate that with OB. See, this is OA, let's say. This is OB, and this will indicate current phasor IR, or the current through the resistor. If you look at the neat sketch up to this, you will see this OA will indicate the voltage phasor V and this OB will indicate the current phasor IR. Now see, in case of a capacitor, see, if the current is IC and the voltage is VC, in case of capacitor the voltage lags the current by an angle of 90 degree. That means if I take VC here, the current IC will lead the voltage VC 90 degree. That means 90 degree ahead of the VC. Okay, so here the voltage across the capacitor is V and the current through the capacitor is IC. Therefore if I want to draw IC will be in this direction because V is here, so IC will go in this direction, and we will indicate that with OC. Okay, if you look at the neat sketch up to this, our vector diagram will look like this. This is OA, which is indicating the voltage phasor V. This is OB, which is indicating the current phasor IR, and the OC is indicating the current phasor IC. Now see, we indicated the reference phasor IR and IC. After that we will draw two additional equal vectors or equal phasors to draw a parallelogram. See, from this point I will draw an equal phasor. Let's say that is CD, such that the CD is exactly equal to OB and the direction of CD is exactly in the same direction as OB. That means I can say CD is equal to IR. I will draw another equal vector from this point, that is equal to BD. We will draw BD such that BD is exactly equal to the vector OC. That means BD equal to OC equal to IC. Okay, so this will indicate IC and this will indicate IR. See, by applying Kirchhoff's current law at node A, we got that total current I will be the sum of IR and IC. This is current IR, this is current IC. If I join this O and D, that means OD, IR plus ID will be equal to I. That means this OD vector will indicate IR plus IC. Or if I go in this way, this is IC and this is IR. In the same way, I will be equal to IR plus IC. So if you want to look at the neat sketch of the complete Phasor diagram, you will see this will be our Phasor diagram of parallel RC circuit. Okay, this diagonal of this parallelogram will indicate the total current. Okay, now look here, this is our reference phasor V, or total voltage V, and this is our total current I. Here the angle between the I and V is phi. Phi is the angle between the voltage phasor V and current phasor I. It is obvious that the current I is leading this voltage phasor V by an angle of phi. Therefore in the circuit the power factor will be leading because current is leading the voltage. Now see, if you look at this OBD triangle, OBD, this will be a right triangle. Therefore the tan phi will be equal to height over base. Here height is BD and base is OB. Tan phi equal to BD over OB. Here BD is equal to IC and OB is equal to IR. Now see, we know that the magnitude of current through the capacitor IC is equal to V over XC, and the current through the resistor is V over R. Therefore this V and this V will get cancelled, and if I put the value of XC, which is equal to 1 over omega C, I will get tan inverse 1 over omega C over 1 over R, which will give us the power factor angle or the phase angle between voltage and current equal to tan inverse omega RC. See, this is our power factor angle or the angle between the total voltage and the total current. Therefore we can easily calculate power factor of the parallel RLC circuit by using this formula, cosine phi or cosine into tan inverse omega RC in case of parallel RLC circuit. So this is the phasor diagram of RC parallel circuit. Now see, here we have two right triangle. One is this OCD. Here this angle will be phi. Therefore the base will be CD, which is equal to IR. The height is OC, which is equal to IC, and the hypotenuse of this right triangle will be OD, which is indicating the total current I. As we are drawing this right triangle using the currents IR, IC and I, this right triangle will be a current triangle. Now look at the triangle OBD. This angle is 90 degree. So this will be another right triangle. In case of this triangle, the base OB indicates IR, BD indicates IC, and OD indicates total current I. As we are drawing this OBD right triangle using the currents IR, IC and I, this will be another current triangle. Now I will show you how to draw the admittance diagram from these current triangles. See, in case of this OBD right triangle, OB is equal to R. We know that IR is equal to V over R. If I divide this IR with V, I will get IR over V is equal to 1 over R, which is equal to G. This BD is representing IC. IC is equal to V over minus JXC. If I divide this IC with V, I will get minus JXC 1. Now see, minus is equal to J square, and here we have J into XC is 1 over omega C. Therefore you will see we will get J omega C. That means I will get J B C. And in case of total current, I is equal to V Y. If I divide this I with another V, I will get I over V equal to admittance Y. That means this OD will indicate the admittance Y in case of admittance diagram. This BD will represent JBC, and this OB will represent conductance G. If I divide each side of the current triangle with the voltage phasor V, similar case is applicable in case of triangle OCD. This OC will indicate JBC because it is representing IC, and this CD will represent G. Okay, so if I divide each side of the current triangle with V, we will get admittance triangle. This OA will indicate G, this AC will indicate plus JBC, this OB represent plus JBC, and this BC will represent G. Therefore you will see triangle OAC will be an admittance triangle, and triangle OBC will be another admittance triangle. Okay, that's it. Thank you.